Start, please.
Thank you. I would like to present our research dedicated to the development of an information system of flexible bionic limb on behalf of our team. In the process of human development, the upper limb underwent the most specific alterations and reached incredible functional perfection and anatomical structure. At present time, there is a great demand for various advanced prosthetics aimed at emulating human hand via muscle activity sensors and electric drives or servo motors embedded into the device. It is safe to say that this area of engineering studies is highly relevant and rapidly growing. However, there are several considerations to take into account when designing a bionic limb, such as complicated activity detection caused
Sorry,
by.
we see the first slide. Please use a full screen mode because we see in the preliminary preview.
Uh-huh, excuse me. Can you see it now?
No, you shared only the window, but not entire screen. If you will share the entire screen, it will solve this issue.
Thank you. Can you see it?
Yes, thank you.
Mhm. Sorry about that. So, complicated activity detection caused by low amplitude of muscle impulse, about millivolt range. Binary analysis of the muscle impulse. It means that typically circuit either notices or does not notice an impulse without paying too much attention to its magnitude. Limited mechanical motion caused by imperfect designs of servo motors and main bodies of the existing limbs, and the complexity and high production cost of electronics as well as the mechanical body. The main purpose of this research is to provide suggestions for possible improvements to many of the existing designs and showcase a mechanical limb prototype developed by the team. The main objectives of the work include implementation solutions to some of the mentioned issues, development of a computer simulation of the prosthetic logical circuit, and the development of a prototype device and its overview. First, mechanical complexity reduction. It is proposed to use flexible materials for the fingers themselves rather than relying on a large amount of joints, as many other designs incorporate. By using elastic synthetic materials for the fingers, the complexity and hence cost of the system can be greatly reduced. On figure 1, you can see a photograph of the developed prototype, mainly the arm. Electronics cost reduction. In order to reduce the cost of electronic components, a standard off-the-shelf AD8232 hard sensor was used, fitted with 3 electrodes. When mounted on an arm, it can output muscle activity data to be analyzed by a low-cost Arduino Uno board. Here is a schematic visualization of this connection. Um, Now, in order to use several AD8232 sensors, one needs a large area of the body due to three electrodes being used for each sensor, which can potentially cause some redundancy in the readings. However, it is not impossible. On this diagram, you can see a schematics of four sensors connected to the Arduino board. They are drawn as potentiometers here. Um, before, before developing a physical prototype, we ran a computer simulation. On this slide, you can see a yellow voltage peak emulating muscle activity, which must be registered by a sensor. Um, in order to attach the electrodes, you must first choose a designated muscle, attach two electrodes to it, yellow and green, as you can see on the illustration. One at the top of the muscle, another at the bottom, and the third red electrode serves as the grounding. It must be connected to a less muscular part of the body, preferably the back side of an arm. In order to interpret the signals, a custom C++ program was developed in Arduino Integrated Development Environment. The graph below visualizes the peak detection algorithm. Here you can see two peaks representing two uh, muscle spasms, and the readings have been linearized in the Arduino IDE due to not very high frequency of measurements. In order to realize finger movement, several servo motors were used, one for each finger. Here you can see their schematics, and each voltage peak triggers a movement in all servo motors simultaneously. For example, the first peak causes a clamping motion. Now the hand is clamped. In order to return it to the initial state, we must administer a second peak. The written program on C++ can be visualized using this algorithm. We start with voltage peak detection. When it is detected, the angle of rotation is checked to be less than 90%. If it is not true, program rotates servo motor until the condition is satisfied. Once it is satisfied, program delays for 0.1 seconds in order to distinguish between different peaks. And the algorithm for a single clamping motion ends. On this photograph, you can see our final version of the device. And now I invite you to watch the short video about the Bionic limb. So once we have connected it to the hand, you can see on the graph voltage peaks caused by muscle activity, and they relay to the motion of the fingers. As you can see on the background, the voltage peaks are linear. They appear linear, although, of course, they are not. fully linear by nature. However, for the purposes of this simulation, such algorithm has proven enough. And here we have a table showcasing the amount of fingers that we actually require for everyday tasks. Such a simple task as holding a glass of water generally demands all 5 fingers activated, while something more precise, for example, pressing a button, may be done with only 1 finger extended. Conclusions. Several challenges related to the development of bionic limbs, such as unsatisfactory sensor accuracy, overly complex mechanical design of the finger section, and high manufacturing cost, have been discussed in this paper with possible solutions. Such qualities of bionic products as low cost, convenience, reliability, and high mobility are priorities in the modern era of prosthetics. Besides amputees, people with limited abilities are also sometimes prescribed with using external prosthetics aimed at simplifying and optimizing everyday movements. And this area too provides opportunities for potential implementation of the provided research. Other possible applications include soft robots, which occupy less volume than their full metal counterparts do and fit in tighter spaces, as well as textile industry. Uh, Thank you for your attention. If you have any questions, I would be happy to answer.
Thank you for your report. It's too relevant and too interesting from the practical and scientific uh, uh, maybe sides of and more points of view. And please, questions. Questions, please. Okay, if no question, I will I will ask the question. Slide 11 and figure 7, and the question is following. It's really interesting. I hope that you will improve the current implementation with the printing, 3D printing of the prototype, and improvement of the servo motor and replacement of the PCB of Arduino by the dedicated microcontroller, or maybe the same but with a wide connection to avoid the problems in the connections and connectors. But this is a fantastic prototype. And the question is following. Did you consider the possibility of adding of some transistor on the power lines here of server motor of SG19 to disconnect it from the power if there is no activities, because the actuators after the switching on the power will implement the signal from the microcontroller and will return back to the same state or change it to the newer, but during the waiting or idle mode you can save the power significantly. So did you consider the adding of transistors here to the power connection lines?
Thank you for your question. This was definitely a consideration. However, we have not yet gone forward to implement it, actually, due to the desired simplicity of the first prototype. However, it is indeed a great possibility for future improvement, and the power saving of this method was not actually considered before, only the simplification of the circuit.
Okay.
But it will definitely be implemented in the future. Thank you for your suggestion.
Well, I hope that we will see such implementation and new investigations. Thank you. You can stop the sharing.